Okay. Hello, everyone, and thanks for joining the developer conference, Lattice Developer Conference 2023. Today's subject is FPGA power consumption or power optimization techniques. This is a follow-on section to follow-on presentation, follow-on training to the previous one we've done today. And we're gonna talk more about architecture and strategic decision that Lattice made for low power, and also techniques in terms of the design techniques to optimize power for your specific design. So my name is Moraz Akama. I prepared the content of this training. I will be going through the slides today. I currently part of the Lattice Insights training platform. Sorry about that. As a content developer and a training instructor, I have been in the semiconductor industry for more than 20 years, 15 of which are with Lattice. And my main field of expertise is Lattice hardware and software, FPGA architecture, design techniques, and best practices, as well as timing constraint. Actually, there's another session about timing constraint that I cover today. I have a WE background and master degree in microelectronics, as well as an MBA in management from the University of Quebec in Canada. Let's get started. So the agenda for today has 3 sections. So we're going to start with the Lattice FPGA low power advantage. So the intrinsic or the organic low power that is available in Lattice FPGAs and why. We're going to cover mainly the 28 nanometer FD-SOI technology, the 4 input lookup table that is used in the Lattice architecture, and other fabric features that make the FPGAs lower power, up to 75% lower power than competitive devices. And on top of that, there's ways also to improve power even further by using some techniques that we're going to cover. So importance of timing constraints, how do they relate to power, the clock enable or use of clock enable, memory usage, and some of HDL best practices. And we're going to finish with the power calculation comparison, where we compare multiple vendors with the real design that is implemented in each one of respective software platform. So let's start with the first section. So native low power factors. So Lattice devices has been architected for low power. So the main focus for Lattice is to design FPGAs for the low to mid-range FPGA with low power. And this strategic decision has made the FPGAs much lower power than the competition, up to 75% lower power than the competition. You're going to see why. One of the main factors, obviously, is 28 nanometer FD-SOI, but there's also architecture choices that are made to improve the power for the Lattice FPGA. So let's start with the FD-SOI. So fully depleted silicon on insulator, FD-SOI technology, is one of the choices and one of the major choices that has been decided by Lattice to architect their Nexus family, and these contributed a lot in terms of bringing lower power FPGAs. So what we notice is with the shrink in process technology, static leakage current increase for each transistor and become a more significant portion of the overall power consumption. So FD-SOI process node offer a solution to this by adding a buried oxide layer that diminished the size of the conductive channel compared to the bulk silicon implementation. So this technology obviously offer a possibility to apply a biasing voltage to tune the transistor and the characteristic of the transistor for power or for higher performance. Depends on this bias current, you can tune the device to be a higher performance or lower power. So biasing consists actually of applying a voltage just under the box of the target transistor. And by doing so, you change the characteristic of the transistor and their threshold voltage to increase drive current at the expense of higher leakage, or the other way around by cutting the leakage current at the expense of performance. So buck biasing in theory could be utilized in a dynamic way in block by block basis, if you wish. But in Nexus platform, this is not something that is possible. You should either have the full device as a low power or high performance. Actually, these for the same part number, and by software programming, you could tune the device for low power or high performance by tuning this biasing current. So on top of all these advantages, it has been proven that 28 nanometer technology offer a much higher reliability with a very low software error rate, as we're going to see in the next slide. So we have done benchmarking of the Nexus family versus competitor devices shown, and we've shown that the power advantage could be up to 75% compared to similar competitive devices from other vendors. There is also video connectivity performance that has been improved up to 2x, and we do that by integrating some unique features in the I/O and the architecture to make the support of video connectivity like MIPI interface, CSI, DSI, much more easier to integrate within the FPGA, and hence have a higher performance than similar devices that are in the same segment. And also in terms of reliability, so 28 nanometer FD-SOI offer up to 100%, 100 times better SC or single upset event, single soft error rate than competition. So the other architecture element, I think, that contributes to the lower power of the lattice FPGAs is the selection of LAT4 architecture versus LAT6 that is used by some of the competitor or the competition. So LAT6 is actually much bigger in size. So when we say bigger footprint in silicon, that comes with a cost in terms of power. So it's up to 4 times the size in silicon, but the implementation of designs using a LAT6 may use lower number of logic levels. So you end up with using less of these, but they have a bigger footprint. But at the end, for a design, you will be having lower power overall if you hit the performance that is required with the LAT4 implementation, because LAT4 is lower power. They are also faster, but you need much bigger pipeline or bigger number of logic levels when you use a LAT4. The other probably difference, LAT6 offer more distributed memory versus a LAT4, 64-bit versus 16-bit. So we believe that LAT4 is a very good choice for low density to mid-range FPGA up to 500,000 logic cells. And that's why we adopted the LAT4 architecture for our Avant family that is up to 500,000 lookup table. We still benefit from having a low power by using the LAT4. So other device architecture elements, so all the families that we see here, so Certus NX, Certus Pro, and Mac Exo family, all the Nexus family of devices, they have also features to allow you to keep certain portion of the device in shutdown mode or in low power mode. So like PLLs, we have a keep PLL in reset, so the VCCU off. So there's a pin that you enable that you toggle to be to put the PLL in a standby mode, so it minimizes power consumption. In the large RAM, there's similar functionality such as the internal memory with this DPS_I pin, the ADC also, and for the I/O banks, especially the bottom bank, we can turn off all the referenced voltages and differential input to lower the power of the device, the overall power of the device. So obviously, when you use any of these techniques or any of these features in the power calculator, as we've seen in the previous session, there is an EF factor that allow you to provide a percentage of time that these blocks are active, so it accurately represents the power consumption or provide you the power calculator, or provide you the power consumption of your device. Plus the, as I mentioned before, so the ability to switch from high performance to low power mode. So if you open the Radeon software and go through the selection of the device, when you select the device, you select the different speed grades, you're going to notice that for the same speed grade, there's a low power version and a high performance version, which allow you to switch between these two modes by selecting one of these devices. It's the same exact part number, but the power profile or the performance profile will be different. So selecting the right device is important to make sure that you have the appropriate bit stream that correspond to your design. So on top of these architectural decision or strategic decision that us had made to improve natively the power, there is also other things that you could do in the design to achieve low power through some design techniques. We're going to cover some of these: timing constraint, clock enabled, memory usage, and HDL best practices. So why timing constraint will have an impact on power? So the timing constraints are very important because these will drive or will guide the synthesis tool and the map place and route tool in implementing your design. And these tools are timing driven. So if you have a high target in terms of performance, the synthesis tool tend to replicate logic, and when you replicate logic, you generate a bigger design which will consume more power. On the other hand, under constraining the design or not constraining the design could have the same impact, because any paths that are not constrained will by default be constrained to 200 megahertz. So you have to make sure that all your timing paths are constrained, and actually there's a session about timing constraint that we covered this more in details. And ideally, you should shoot for 100% timing coverage to make sure that you have you don't have a non-expected behavior of your design, because paths that are not constrained mean there is no target for the software to constrain them against. And then they will be defaulting to 200 megahertz, and they will be probably generating a larger amount of logic that you may not need because they need to run at a very low frequency, to have 20 megahertz or 25 megahertz. And that so that is important. So timing constraints have a big impact in terms of the logic generated, in terms of the amount of resources that will be used in the design, and making sure that you have a good design coverage is important in order to not overstate or understate your design resources. I mean, I put here target is 90%, but I think you should shoot for 100% timing coverage. I mean, making sure that all your timing paths are covered, and this will guarantee that there's minimal discrepancy between what you see in the simulation, function simulation, and hardware behavior. So non-constrained path could create intermittent problems in hardware. So it's very important. So Clock enable. This is another important factor that need to be controlled. So remember the dynamic power is the C multiplied by V squared multiplied by the frequency multiplied by the activity factor. So obviously the activity factor, as we've seen in previous session and other session, has an impact on the overall power consumption, but also the frequency. So if you can reduce the frequency or the frequency at which each block is operating, if a block is not functional, disable the clock. That will minimize the power consumption. So try to use clock enable instead of generating new clocks when possible is also a good practice. So instead of having 2 clock trees, you may have, or 10 clock trees, you may have only 5 clock trees, because clock trees have a clock, they distribute the clocks, and if you have more clocks, then there's more power that is needed to distribute all these clocks across the board. So using clock enable is a good practice in terms of power, but also in terms of timing closure. It's better to have 5 clock domains to achieve timing closure than having 10 or 20, or some designs may have even larger number of clocks. And usually they are related to, some of these may be related to each other. So if you use clock enable, like if you're going to divide by 4, use clock enable from the main clock with the DCC, which is dynamic clock control unit that is part of the lattice architecture, to disable the clock 1/4 of the time, and that will provide you a divide by 3 or by 4 clock, instead of having that clock going through a PLL and generating a different frequency clock. And also the architecture integrate clock enable resources, like we've seen in the previous slide, and also all the slices or logic cells integrate clock enable resources, and these could be used efficiently to minimize the routing and to minimize also the power consumption. We've seen we talked about the block enable, the use of clock enable to control the clock distribution on the fabric. So do not disable the use of clock enable in the synthesis option. So when you disable this, that probably prevents some optimization to be done in terms of using the clock enable. We talked about DCC and DCS. So there's these 2 primitives that are part of most of the lattice FPGA architecture. DCC is dynamic clock control. It is a primitive that allow you to shut down the clock on a certain portion of the design. So you could literally control the clock distribution across the device, and there's a lot of these in the device. I mean, some devices have up to 64 of them. DCS is dynamic clock select, so you could switch between 2 clock domains using the DCS without glitchless switching between 2 clock domains. And you could have a low performance and high performance clock, and then switch between the low performance and high performance. When you don't need the high performance clock, you have all your design running at a lower performance one, just to monitor the traffic that's coming in. So that's another way probably to use to minimize the power consumption in your design. In terms of memory usage, so low power memory usage. So usually what we have in implementation, in this case, we have a dual port RAM with a read port and write port. And if there is no specific information in the source code, the clock enable will be always tied to 1, and the write enable and read enable will be controlling the write access and read access to the memory. And by keeping the write enable always tied to 1, you have all the logic inside the memory that is always toggling, and that's an extra power consumption that you have in your design. So a better way, or some lower power implementation, is to have the write enable tied to 1, and the clock enable is just enabled when you have a write access or read access. So these implementations tend to have a lower power efficiency than having the clock freely toggling in the block, even if there is no traffic to the memory. Obviously, there is extra logic that need to be implemented, like state machine, to make sure that you control these signals. But still, if there's a big amount of memory, then you end up with a lower power implementation for your design. The other way to do the same thing is to use the DCC or dynamic control, dynamic clock control with the DCC unit, and have an FSM that control this write clock and read clock and only enable it when you need it. You may be accessing the memory 50% of the time, not 100% of the time. That's a 50% saving on the power by disabling the clock to these blocks. So when it comes to HDL coding, so the way you write your HDL code or your source code matters in terms of power consumption. There is a difference. Even functionally, things may be the same. There's a difference between using the case statement and if-then-else statement. So if-then-else create a priority decision. I mean, usually these happen if there is undefined cases. Then all the others will have lower priority and will create extra logic and will be generating priority tree, and that's an extra logic levels or logic that is generated based on the way you create your HDL code. So the first option, the first statement will have a higher priority than the second one, then so on. If you do a case statement, they are all evaluated at the same time and they have all the same priority, and there is no extra logic that is used. So case statement is better for hardware implementation unless you need priority between the different the different cases that you have in your design. Also FSM encoding, so for finite state machine encoding, the type of encoding will have an impact on power. I mean, gray or one hot encoding should have a lower power consumption than sequential or binary implementation. And the reason is that in gray implementation, only one bit changing between states, so less transition, meaning less power. And one hot, you have only 2-bit changing between states, so less decoding logic also. So in this case, you may have decoding logic, a little bit more logic, but you have less transition. In this case, you have more bits, but only 2 bits changing between each state. So by using one of these encoding, you kind of have a better opportunity, or an opportunity to improve power also. So the other factor that I will highlight here is the use of a clean reset or preset strategy. So making sure that the resets are consistent through the design. There's another training about reset. It's a big topic, but reset usually are high fan-out signals, and having multiple of these in your design, having them globally distributed to the whole design can create a lot of routing congestion, but a lot of power related consumption. So having a clean, consistent reset strategy should be also another thing that you could do. Last and not least, minimize the number of combinator logic. So we've seen in previous presentation about the power calculator that the power consumption has two components, or the activity factor has two components. These are components related to synchronous logic, and these components related to combinator logic. And the combinator logic is very hard to predict, but it could be even higher than 100%. And the reason is that this type of logic usually create glitches. So if you have an AND gate and one pin coming from an external word, another one that is coming from internal FPGA logic, it takes a noise glitch on that external pin or a difference in the time these two signals change, that will create a glitch, and that's also a transition. So if you have a lot of combinatorial logic, that will create a lot of power also that is consumed, that is not necessarily. So by synchronizing your logic, you minimize the impact of combinatorial logic. So that kind of concludes the low power by design section. So to summarize previous two sections, so like we said, Lattice is a leader in low power, and when it comes to FPGA architecture and device offering, all the devices are architected for low power. We have that as a strategic goal, and making sure that we design our device from the ground up to be low power, instead of scaling down probably higher end architecture to a lower end FPGA. The HDL practices will be an additional level of power optimization that you could use in your design to minimize the power consumption. In this last section that we're going to go through the power calculation comparison, we're going to have some design examples where we're going to focus on memory intensive design, register intensive design, and DSP intensive design, and try to see with some generic code that is exactly the same between the different vendors, implement that in different technology, and see the impact, the power calculator output for each one of these vendors, and compare the results. So the first design is a memory intensive design. So we have here is a dual port RAM with some counters for generating the write address, the read address, and the data generated to be written into the memory. And we have an FSM that control all these counters and access to the memory, and then output the memory goes to an output pin. So the memory has been defined in source code, not using any primitives from any vendor, and it's inferred by the synthesis tool to the block that is use it for to the block for to the primitive block for each vendor. So it's a parameterizable design, and we have replicated that 100 times into each one of the three vendors. So if we summarize the whole thing in this matrix. So the just first what software version we use it. So we used Radeon 2022.1 from Lattice, Vivado 2022.1 from AMD, and Quartz from Intel 21.1.1. So, and the device that we selected from each one of the vendors. So for us, we selected Certus Pro NX100, which is 100,000 logic cells, 96,000 logic cells precisely. And for Xilinx, we used the XC7 Series 100, which is 100,000 logic cells equivalent. So it's a lot 6 based, but the equivalent device is the logic cell equivalent is 100K. And for Intel, we used the Cyclone 80, and we used the low power version for each one of these. They are similar package offering. For Intel, we have a logic element, 81K logic element with 29,000 ALM, because the architecture is a little bit different. So we have the naming of resources different, but they are fairly equivalent in terms of the size. We have a frequency. The design will be running at 150 megahertz, and the activity factor is 12.5% for each one of these. So we have the default activity factor for all of them to be 12.5 megahertz. And ambient temperature is 25 degrees. Board, we selected GDEC board with the power calculator. It's very close board between the two vendor, and airflow of 200 also. And in terms of resource utilization, you're going to see each one of these designs in terms of memory usage. So we have 1.8 megabit of memory used on all of them. The configuration or the size of the memory blocks are different for each one of them. So for the Lattice, we have an 18 kilobit, so these 100 of them that are used. In terms of Xilinx, they are 36 kilobit blocks, so 50 of them are used. For the Cyclone, it's 200 blocks because they are 9 kilobit block. And in terms of lookup table that are used, or logic cell, logic element, a very comparable number of resources. I mean, 5500 is LAT 6 usage, but LAT 6 is the factor that they use to generate the logic cell equivalent is 1.6. So if you multiply that number by 1.6, you should end up around 9,000 lookup table. In terms of flip-flops, the number of flip-flops that we have here for each one of the implementation, the number of IOs is the same. So the end result is that we have much lower static power from Lattice with 34 milliwatt of static power, 177 from the other two. Dynamic power lower also for the memory, much lower than the other two implementation. And for IO pre, similar, probably this small variation. So in terms of total power for memory intensive, we end up with 275 milliwatt for the Lattice implementation, 555 for the Xilinx implementation, and for Intel 484, which represent around, 200% and 176% higher power for this for Lattice implementation versus the competitive implementation. So all IOs are being single-ended and 1.8 just to minimize the difference in terms of the IO power consumption. So the second design we have is a shift register. So we have a very long shift register, parameterizable HDL, also with the a 64-bit shift register, and the depth of the shift register is 500, and the same code has been implemented same way for each one of the vendor, and we're going to see the result of the implementation. So software tools, the same software tools, the same devices are used on the 3 variant of the implementation. The frequency is 100 megahertz in this case, activity factor is 12.5, same board, thermal profile that we used before. And you can see in the implementation, a number of flip-flops is 3200 for this. There's no lookup table. We use it. The number of IOs is 130. And again, static power, much lower than the other two guys, 49 milliwatt versus 97 and 77. Dynamic power and IO power, and the total power 207 milliwatt versus 241 and 295, which represent, 143% and 116% of the Lattice power. So depends on the implementation. Obviously, the power consumption is different, but just trying to go through different example of implementation from different vendor. So the third example we have here is the DSP intensive design. So we have an 88 top FER filter, 16-bit data and coefficient. And in the Lattice implementation, we have 2% usage on register slices, lookup tables. And in terms of DSP usage, we have 56%. And that's the intention, is to make sure that we focus more on the DSP side. So generic design, we implemented in 3 different vendors, and the synthesis tool will infer the primitive for each one of them. Same devices used, frequency 100 megahertz, activity factor 12.5%, same thermal profile, and this is the resource utilization. So we have 88 DSP, 18 by 18, Depends on the vendor. Like for Xilinx, they are different size, but they will be configured to be 18 by 18. And number of slices, logic cells or slices or ALM used for the same implementation, number of flip-flops, number of PIOs, and static power. Static power is 37 milliwatt for Lattice, whereas we have 97 and 77 here. Dynamic power and IO power, and then the total power, and we end up with a 188 milliwatt of total power compared to 239 and 217 milliwatt for the Xilinx and Intel implementation, which represent 127% and 115% of the Lattice power consumption. I mean, and this is mainly related to the way the devices are architected, the technology choices, all what we've seen in the previous slides in terms of the technology choices for the low to mid-range FPGA. So if someone doesn't require the higher performance of the much larger devices and can fit within the scope of the device offering that Lattice has, can benefit from this power advantage that we offer through the architecture of the device and the selection of the technology process and other factors that we integrated just to make sure that our device stay as much lower power as possible, as we've seen up to 75% lower power than the competition in terms of benchmarking. So in terms of reference documents, so there's a lot of documentation that is available to you to have deeper knowledge about these subjects. So the power manager technical notes that are downloadable from the web. There is a thermal management technical note that is available. There is the Nexus family device data sheet. In the Lattice Insight training portal, we have training about the design techniques, about the design migration between different vendors. There is the help menu that is available in Radeon and Daemon, and all this will allow you to have better insight in terms of the subject. Again, this is subject that could be covered in much more time, but to try to kind of summarize everything in this presentation to give you some insight in what type of training and information that could be available from Lattice. Please sign up for free on the Lattice Insight portal to get access to all the trainings or pre-recorded trainings that are available. And on this portal, you can go to latticeinsight.com and you can sign up for that. And that kind of conclude the presentation. So let's go through the summary. So I mean, we're seeing Lattice FPGAs are up to 75% lower power due to architecture, process, technology choices. So it is a strategic focus for Lattice to offer the lowest power FPGAs and architect these devices from the bottom up to be low power. And in fact, we offer up to 75% lower power than the competition. A lot of customers are impressed by that, but try it out. So we sometimes we don't think that timing constraint could have an impact on power. We've seen that in fact timing constraints are important in terms of power optimization. So making sure that you have a high coverage, timing constraint coverage for your design, and not under constraint or over constraint your design, making sure that you have your timing constraint set properly. Like I said, there is another training about timing constraint. I hope you can join that one so you can have more insight in terms of timing. It's a very sensitive subject, and there's a good, interesting training that we'll be covering today. There is a timing closure training also that is covered by one of my colleagues, Sukrath, that goes also in terms of how do you make sure you can close on timing and cover, have time closure for your design. So the other thing we've gone through is the HDL code. Obviously, the way you write your code will have an impact on power. These architecture hardware feature that will allow you to optimize power. So make sure you take use of the clock enable or the DCC, DCS that are part of the architecture. Make sure you have the clean reset strategy, the clock tree, minimize the number of clocks that you have in your design, the FSM encoding, combinatorial logic, try not to use any combinatorial logic. So every single piece adds a little bit. So having a clean and clean design and well-structured design following some guidelines should help you in terms of optimizing power, even though the latest devices are very low power. So we've seen that through examples, so low power advantage versus the competition, and we've seen that through some examples that we ran through. So that concludes the presentation. So now take a look at the questions that we have. I'll just give me a minute. And if you have any question, please use the Q&A widget to ask them, so we can make sure we answer these. So so the first question that I see here, so you mentioned that Lattice offers up to 75% lower power than the competition. What is the basis of this number? So this is actually based on some benchmarking we have done using different type of designs and implementation that we run through the tool and compare the different tools and compare results. Like the examples that we've done in here, but these are more like specific to certain architecture element. We don't use this to do the benchmarking. We use real designs to do the benchmarking, and on average, the 75% lower power to the advantage of Lattice. That's what has been identified. And I mean, as you know, power consumption is highly dependent on the customer design and architecture and so on. So we have to kind of do some statistic to make sure that we have a representative number in terms of lower power. So the next question I see. So what is timing coverage? Good question. And I think I highly recommend if you can attend the timing constraint session. That will give you a very good insight in terms of the timing coverage. And it's basically an indication of how many of your timing paths has been covered by timing constraints. So a timing path is identified as any flip-flop to flip-flop connection within the FPGA, and ideally you have 100% of them covered. So this percentage will represent how many of the paths that are identified by the tool are being covered or constrained in your design. And like I said, there is much more details in the session about timing constraints. So please, if you can join that session, that will give you a good insight on this topic. Okay. So another question, how much power saving can you expect when applying one of the clock enable memory access technique? Yeah, I mean, this is a good question. So, I mean, it's really dependent on the usage of the memory. For sure, there is power advantage, but how much power advantage, it really depends on the memory access, how much what is the percentage of memory access that you have in your design? How often do you access your memory? If it's 10% access time, then 90% of the time you could shut down that memory block and save power. In the designs that I tried, you probably expect 5 to 10% advantage by power saving by just using that technique. But it's really depends on the design, how much memory you have, what's their configuration, how many of them are active at what percentage of the time. So it's all dependent. I think if you do a power calculation and you have the proper logic to control the clock enable on this memory, you should see some saving in terms of power. Another question. In the competitive analysis, we see up to 200% higher power from the competition, whereas you mentioned Lattice offers 75% lower power. Can you elaborate on the numbers? Yeah. I mean, like I explained previously, I mean, the 75% is benchmarking that we've done over more realistic designs, real designs that we have. What we've seen in the last section of this presentation is more block basis power consumption. So what I try to do is identify blocks and have a high percentage utilization of each one of these blocks to see the impact of power, the impact on power from different vendors. And that's where you see the 200% higher power from one of the vendors versus the Lattice implementation. In a real design, you have a mix. You have memory, flip-flops, DSPs, logic. So there's a mix of all these components that we've seen in the last section, and that may average up to 75%. And that's kind of the benchmark that we've done to just to compare our numbers to the competition. Okay, I think that's about it. If there's any question, please post in the chat. Even if I don't answer in this session, I'll try to get back to you on all the questions that we have. With that, I want to thank you for your time. Thanks for being part of the developer conference, and I hope you're going to join other sessions that we have today and for the full 3 days. And have a great day. Thanks.